Okay, what's next in Earth's history and the evolution of its climate? Now we can say something about it because once I get the pointer up, you can see what I mean. What my computer is getting old, so it just doesn't do the right. Anyway, so we talked about all the so-called evidences of past climates that are locked up in the tree rings, in the corals, and in these shelled animals that can be found at the bottom of the ocean, in the ice cores and the gas bubbles in the ice cores, and so on. Past climates are called paleoclimates. For simplicity, you can say PALEO climate, but the original English spelling seems to be PAELEO, paleo climate. So it's the past climates, and these evidences locked up in various things are called paleoproxies. Why are they called proxies? Because when we say we can use oxygen isotopes to estimate long ago ocean temperatures, it's not a thermometer that gives you exact temperature. It just tells you that because the oxygen isotope is in this way or that way, temperature must have been cooler or warmer than the present. So you are estimating some change in temperature at that time, and hence it's a proxy for a temperature. If you don't know what a proxy is, you can ask your teacher or parents and so on. PROXY is something that stands for something. So paleoproxy for temperature means it's an indicator of temperature, not exactly temperature itself, but they are very reliable reconstructions, they are called. So we can go back in the past, find these evidences and reconstruct the past temperatures for which we don't have direct measurements. So in the beginning, 4.6 billion years ago, when the solar system and Earth first formed, it was at its absolute hottest. The temperature was likely more than 3,600 degrees Fahrenheit. That's really, really hot. Scientists are still learning about young Earth because we keep finding evidences and new ways of analyzing the past and so on. First, it is supposed that a giant cloud of gas and dust spun through the First, it is supposed that a giant cloud of gas and dust spun through space. Rocks, dust and gas collided. Gravity kept these bits and pieces together. Sun was already there, and sun's gravity was hurling things around itself, and the things that were hurling around were colliding, and they were all gravitationally bound together. If you don't know what gravity is, you will have to learn it from your teacher or another video and so on. And you have something with the mass. It attracts other masses, and that's called gravity. If you remember Newton and the apple falling and all those good stories, then you know something about gravity. The chunks grew larger and rounder, forming Earth and other planets in our solar system. As you know, there are other planets and lots of moons of the planets, and asteroids are hanging around and so on. They all circled a much bigger glowing ball of gas we call the sun. All those space collisions created great heat. Earth was too hot to have a solid surface in the beginning. Instead, seas of melted rock covered the planet. Hundreds of millions of years passed, and the Earth began to cool. The planet shifted a bit in its orbit. It traveled around the sun at a slightly different angle than it is now, because as it continued to grow and solidify with its inner core, that's a liquid and so on, its angle has changed over time. Because of this, Earth began to have seasons. When it tilts, as you know from your orbital mechanics or your introduction to Earth's orbit, as it goes around its orbit around the sun, the North Pole will be pointing towards the sun in one season, and the South Pole will be pointing towards the sun in another season. So you have winters and summers. So seasons were created. Okay, so uh, we were here, rain fell as the seasons formed, because as we already learned, when there is heating and cooling, air is getting warmer and rising and expanding and cooling, and rain falls, snow falls, and so on and so forth. Oceans formed in the meantime, and earth cooled even more. Masses of land developed that we call continents, and they were not all where they are now. They used to be in different places, and there were also many volcanoes all the time along the Earth's history, and we have still very active volcanoes that are always going off. Some are under water in the Pacific Ocean and so on, and some are on land all the way from Indonesia to Iceland and so on. So what do volcanoes do to climate? Here is a nice schematic of a volcano that is going off and throwing ash, dust, chemicals and so on into the air. Can be thrown tens of kilometers depending on how strong it is, and you can see here the magma flowing down the slopes of the hill. Volcanoes release CO2, which is a greenhouse gas, during its eruption, during their eruptions, and also from underground melted rock that seeps through the cracks. Right? Volcanoes release CO2 during the eruptions, and also from underground melted rock that seeps through the cracks. Compared to millions of years ago, there is much less volcanic activity today because the continents have stabilized and a lot of the cracks in the rocks have closed down and so on. Yet, erupting volcanoes still affect climate. Spewing ash forms a haze that blocks the sunlight and reduces the albedo as well, causing a temporary cooling. So that's a different effect. Blocking sunlight as opposed to reflecting sunlight just allows less of the energy from the sun to reach the earth and into the atmosphere, and thus ends up cooling the climate. The ash clears within a few years, but the volcanic CO2 and its warming effect can last much longer. So throughout Earth's history, volcanoes have played a role, and they still continue to play a role. So at that point, Earth was still very hot, as even though it has cooled for millions of years, most likely more than 400 degrees Fahrenheit. From 3600 it had come down to 400. So great lot of cooling, but still very warm. Humans couldn't have survived in these temperatures. Also, the atmosphere had no oxygen. Can you believe it? At some point, the Earth's atmosphere had no oxygen. So if any life was there, it was going to be in the mud where some oxygen could have been available, or they were surviving on methane, or they were producing methane, or they were in the oceans, which have already had formed, and ocean water would have had some dissolved oxygen in it. Still, one simple form of life did develop, a kind of bacteria living in the oceans. The bacteria gave off oxygen, so Earth had beginnings of breathable air, making way for different forms of life. So ocean water had oxygen, and bacteria were already doing some chemistry to survive, to produce their own energy and reproduce and so on, and they were producing enough oxygen. And remember that if the oxygen builds up in the water and there is no oxygen in the atmosphere above, then the oxygen will begin to come out. How do you think about it? Well, think of a can of soda or thumbs up or something. It is cold and it is closed, so you know that it has some CO2 inside. If you open the cap, then the air, which has much less CO2 than the thumbs up will begin to release the CO2 into the atmosphere. Similarly, if the ocean builds up a lot of oxygen from these bacteria, then the atmosphere will begin to get some of that oxygen coming out of the ocean. Okay, then the climate changed. It changed many times along the way, but we are simplifying things here. A snowball Earth developed, which means right now you have glaciers in Greenland and Antarctica and some mountains, but glaciers came all the way down, let's say, into where now Africa is, where India is, and so on, where the Philippines is, and so on. And what happened next? Maybe all that new oxygen replaced greenhouse gases as the snowball Earth evolved, cooling the planet, or maybe there was a lull in volcanic activity, so CO2 was reduced greatly. Either way, scientists have found glacial rocks and other evidence of ice in every corner of the world, from North Pole to the South Pole and from South Asia to South America, which means we did some detective work already. Somebody did, and they say there was ice down to very low latitudes, which doesn't exist now because low latitudes are very warm. Okay, we jumped many steps. You can find out more if you're old enough to go and look at my course called Earth's Climate, Past, Present and Future, and there are lots of details like this in my course. Here is a snowball Earth schematic which is showing lots of snow in the atmosphere, tall glaciers on land, and sea would be covered with sea ice as well. So then over more time, underwater volcanoes built up under the ice. So even if you put a lot of ice, volcanoes are going off and they are under the glacier, but they spewed gases through the cracks in the glaciers. They became more and more active. New forms of life developed around the volcanoes, just like you have now teeming life around the so-called hydrothermal vents in the oceans around Galapagos and other places where you have sulfuric acid coming out more than 120 degrees temperature, and yet you have life surviving in this toxic water deep below the surface, so there is not even any light. Imagine. These creatures breathed in oxygen and released CO2. This caused the Earth to thaw out over hundreds of millions of years. So snowball Earth built and volcanoes produced these greenhouse effects to trap the thermal energy and then warm the temperatures and melt away the glacier and get us out of the snowball Earth. Okay, so we'll come back and discuss more on how other things happened as we went along and how the climate kept on changing. Okay, maybe I'll find a schematic from National Geographic or so, or British Encyclopedia Britannica, to see if we can do some image to show how the past climates have changed over time. Okay.